Hi, let me tell you about some work that my student Jags and I have been doing. We'd like to take the idea of Bayesian cubature and make it into a automatic algorithm so that all the user needs to do is provide a black box function, provide the error tolerance, and the algorithm returns the answer to within that error tolerance. And we want the algorithm to be practical. We want it to be relatively fast. Here's a team that's been working with me on developing adaptive automatic algorithms. We have developed a MATLAB library that has multivariate uh, integration, cubature, also univariate optimization and function approximation. And now we're working on a Python library, QMCPy, that we hope to release this summer. The algorithms that I'm going to tell you about are part of this library. We want to have an algorithm that approximates the integral to within the error tolerance specified by the user. And we want the user to be able to hand us almost any function and the algorithm will work. Now, the user can't hand us any possible function. It must be a reasonable function. And let me explain what I mean. Think of your wonderful algorithm. You're given a function and it happens to be 0. So you sample until you're convinced that it's 0. Now, you sampled at a finite number of places, and there is another function that is not 0 that could have a huge integral. It could be as smooth as you want. And so if you had been given this other function instead, you wouldn't know. And so there's no way that your algorithm or mine can work for every function. It has to be functions that are reasonable, functions for which when we sample it a reasonable amount of time, we can tell enough about the function to know how many more samples we need to get the correct answer. So I'd like to think of this as the function is coming from an urn. But in our case, we don't know which urn it's coming from because the user hands the function that they want us to integrate. So we're going to have to do some choosing of an urn to match the function, and that's going to be the inference part. Because we're taking a Bayesian approach, we're going to assume that the function comes from a Gaussian process. It's an instance of a Gaussian process, but we're going to put in some parameters that allow us to be somewhat flexible. So it could be this urn that I'm showing you. It could be a different urn depending on what the M and the S and the theta are. We're going to sample the function at n points, and we're going to let n vary. And so our design matrix is going to be n rows corresponding to n data sites and d columns corresponding to d coordinates. F, the vector, is the function data, n values of the function at these endpoints. And then we also need to be able to integrate this covariance kernel or this covariance function that defines our Gaussian process, integrate it once and integrate it twice. This is the scalar from a double integration. This is the vector that comes from integrating once and then putting in all of our n data sites. And then this is the matrix that every possible pair of data sites we put in, and that gives us an n by n matrix. And now this is known, what I'm writing down here. The integral of the function, given that we observe the function data to be y, has this known mean and this known variance. And so what we want to do is make 2.58 times the standard deviation of this, or the width of the credible interval, no bigger than epsilon, make n large enough so that this happens, and then we would seem to be done. Now there's a little more involved in that because we need to choose the m, the s, the theta. So for example, Maybe this is our errand. We don't know until we sample the function. Another problem. We're going to be doing some matrix inversions or solving systems of equations that can be expensive, order n cubed. We want to avoid that expense. And then maybe some ill conditioning. And then let's go back to our original assumption that f is a Gaussian process. Does that make sense? Well, once we've sampled the function, we should be able to look and see. We'll talk about that. So we're going to use the empirical Bayes approach. We're going to estimate the parameters using a maximum likelihood. It's described in this paper. And this is not new. An alternate approach would be to put non-informative priors on the M and the S. It's not so easy to do for the theta. And we can also use cross-validation, but we'll, for this talk, stick with empirical Bayes. And now we see that the mean depends on y, which we expect it should. The variance, or the scale factor that appears here, depends on y, which we also expect it should. And that's good because that means that this credible interval width is going to depend on y. And before it didn't. It didn't directly. And now we see indirectly through S, it's going to depend on y. Theta involves an optimization, which will also depend on the function value data. And we see now that we're going to need to compute determinants as well. Finally, this is our answer once we have our credible interval small enough. And it depends on y as well. Okay. Well, this helps us determine which errand, but we still have to solve the problem of computational cost when n is large. And we still want to look at whether the function really looks like it came from the Gaussian process. So this is an idea that Jags and I introduced a couple years ago. It appears in the paper that I mentioned, and we've extended that idea since then, so I'd like to dwell on the extensions. But to give you the gist of it, we're going to write our Gram matrix in terms of the eigenvectors V, the eigenvalues lambda. The eigenvalues will assume to depend on this theta, but not the eigenvectors. So this is an important assumption. The V needs to be known analytically. The lambda, no, we'll compute that. This scale of 1 over n, the reason why that is because we want our eigenvector, the first one, to be 1, not 1 over root n. This assumption that the integral of the covariance kernel and then putting in all the data sites becomes 1, that's not a crucial assumption, but it holds true and it makes the formulas simpler. And then the big assumption is that when we multiply the eigenvectors, complex conjugate transpose, times any vector, that operation only requires not n squared, but n log n. And that's going to be what we call a fast Bayesian transform. And this kernel, if we can find the kernel that matches the design, so it's a pair, a kernel and a design, and they match to satisfy these assumptions, we'll call that a fast Bayesian transform kernel. So now what happens is we transform the data, and we transform the first column of the Gram matrix, and that gives us the eigenvalues. And with the transformed function data and the eigenvalues, we can now write our optimization for theta as follows. Our credible interval can be written again in terms of the eigenvalues and the transformed data. And as n gets large, this quantity here gets small. There can be cancellation error, but we have a way to get around that we describe in the paper. And in getting large here drives this down, and eventually we get this smaller than or no greater than epsilon, and then we're done. And this is our answer. It's the sample mean, which is maybe not surprising, but the big job is figuring out when n is large enough. And the advantage of these kind of kernels that match these kind of designs are that the cost is order n log n times how many iterations you need for this optimization. So let me show you what those kernels look like. The lattice type we've talked about in our paper. The Sobel type we're talking about now, and we're writing up for publication. In both cases, our kernel, which has two arguments, becomes a function of the difference of those two. This k has to be properly chosen, so this is still positive definite symmetric. And our design is not arbitrary n, but it's a power of 2. Now this minus here is the additive inverse for addition defined in a special way for the two cases. So for lattices, this plus is addition modulo 1. And that works for points that look like this, and you can shift them around modulo 1. That means they go outside the unit cube, they come back in the other side. For Sobel sequences or other digital nets, the plus becomes bitwise addition. And then the fast Bayesian transform is either FFT, in the case of lattice, a one-dimensional FFT, or fast Walsh transform for Sobel. So what can cause us a little problem? Well, when we're doing the lattice node designs, typically what our kernel would look like would be involved with, would involve Bernoulli polynomials of degree 2, 4, etc. Those are the kernels that are typical in the quasi-Monte Carlo literature. So the challenge is that this parameter here, this r prime, has to be an integer. It's discrete. If we write this down in terms of its Fourier series, this r could be anything bigger than 1. So it's not a problem if we look at this representation, but this representation is now an infinite sum, and that presents another problem. So we'd like the flexibility of arbitrary r, but we don't want to do an infinite sum. So here's what we do. We say, well, what do we really need? We really need the eigenvalues, and the eigenvalues are the fast Fourier transform of the first column of the Gram matrix. And if we look what that is, it only depends on this kappa function, not all x, but only x that looks like 0, 1 over n, 2 over n, 3 over n, and so forth. And we could do that with some work using one FFT. And we can afford an FFT. That's only n log n. The details are on a slide that's at the end of the talk. So let's look at some examples. Here's Keister's example. This is an integral over all of Rd. You can transform it into an integral that is on the unit cube. If we use an adaptive Monte Carlo algorithm, it takes 0.14 seconds. It takes 2 million samples. If we use some other algorithms based on the lattice sampling and the Sobel sampling, but that are not Bayesian, you can see it's a big speed up. If we use our Bayesian lattice or Bayesian Sobel, the ones I've just described, in this case, the Bayesian lattice is faster. It's using fewer points. The Bayesian Sobel is a little slower. And probably the speed has to do with the inference. And the fact that this is faster than the corresponding lattice one is not always the case. So what we do need to do probably for our Bayesian algorithms is look into the coding, because they're not quite as fast as we'd like them to be compared to these other algorithms that are not based on the Bayesian approach. Here's another example, Gaussian probability. Again, the Monte Carlo is much slower than the ones dependent on the quasi-Monte Carlo or low discrepancy sampling, the ones that uses the lattice or the Sobel. Here, this time, the Bayesian lattice is slower. The Bayesian Sobel is slower, which is a pity. That's something that needs to be worked on, but they're both much faster than simple Monte Carlo. Now let's turn to the problem of, is this Gaussian process assumption reasonable? Does it make sense for us to assume that our f comes from this urn, which is described by a Gaussian process, even once we've figured out which is the right urn because we've inferred the parameters of the Gaussian process? Is that a good assumption? So what we do is we look at our function data of the random variable, and if we center it, and if we multiply by the inverse square root of the covariance matrix, then we get something that should be IID multivariate normal. We're going to take the observed function data, that's y. We're going to take our inferred m, our inferred s, our inferred theta, and we're going to compute that data. And we're going to look at the QQ plot of that data versus standard Gaussian, and we hope it lines up. So first we'll take a random function. This is a random function that we have cooked up to fit a known R and a known theta using lattice sampling. So this is all done using lattice sampling. And in this case, where we have a randomly shifted data sites, we have a random function. The known R is 1.5. The inferred R is 1.48. I would say that's pretty good. The known theta is 0.25. The inferred is 0.36. A little off, but maybe acceptable. And when we look at this data, it lines up pretty well. This is using n equals 64, so we have 64 points that should lie close to this line. Here's another example. Different random function, different random shifted lattice. Looks maybe not quite as good, but still reasonable. Now we've changed the theta to 1. Here is another case, maybe not as nice. This case is not so bad, and so forth. And if we do this for 9 different choices of R and theta, 3 different thetas, 3 different R's, 3 different thetas, what we find is that the inferred values cluster around the true values, but they're not such tight clusters, okay? There is some deviation, and in this case, I'm not sure why, the inferred R's tend to be bigger than the actual R's. That was a cooked up function where we knew what R and theta should be. Here's an example, the Keister example. We don't know R, we don't know theta. All we can do is try to infer it. And again, 64 points, dimension equals 3. And I would say, doesn't look like it quite falls on the line. Another example, different shifted points, same integrand. So the integrand's not changing, but the places we sample are changing. One nice thing is that the inferred R and theta are similar. They're not too wild. When we go to n equals 1024, it's even more obvious that this is not on a line. So I think it's hard to be convinced that this is a typical function from a Gaussian process. Our algorithm works, but our underlying assumption maybe can be called into question. Here's another example, same integrand, but a different sampling, different shift in our lattice points. So let me sum up what we found. The credible intervals that are used in Bayesian cubature, we can use them to construct adaptive algorithms, and they provide answers, and the answers tend to be very good in our experience. So we like that. What we like even more is that when we do the low discrepancy sampling, we can get a much faster answer than if we were using, let's say, an ordinary Monte Carlo. Now, when I talked about ordinary Monte Carlo, we were not using a Bayesian method. We were just using a stopping criterion based on some earlier work. When we do the empirical Bayes, we're able to choose the right urn, I would say, because the parameters that we get do depend on the function data. And I think that's important if we're going to use the Bayesian cubature to do integration in practice. We cannot just fix the parameters. And in fact, we used a little extra effort to broaden our collection of urns so that we have more to choose from and have a better chance of getting one for which our integrand is typical. The one thing that we have found very helpful to make this a practical algorithm is cutting the cost down from n cubed to order n log n. And we can do that when we can match our sampling, in this case lattice or Sobel, with our kernel. And so we would encourage practitioners to think about not choosing their favorite kernel based on what's often used, but find a way to match the sampling. These are the two cases that we found. Maybe there are more out there, but we haven't found them yet. But they do work well when you choose a kernel and a sampling method to match. So what are some of the challenges that we've run into? Well, our algorithms are not as fast as some others that use different stopping criterion, and this is due to the time it takes to infer. And maybe our coding schemes can be a little faster. We don't know whether we're going to run into a case of overfitting if we introduce too many parameters. We want a rich collection of urns or possible Gaussian processes because we don't know where the function we're going to get handed this from, and we don't want to assign it to some urn that is really an outlier for, but we don't want to overfit. The Gaussian assumption we see doesn't always seem to fit well, even though our algorithms fit well. And I don't know what to do with that, but I think people haven't looked at it, and I think we need to think about it. And then for the lattice sampling, we are using periodizing transformations, and they are not chosen automatically. They are chosen by what we think would work. And that's still a part of our algorithm that is not automatic, and we would like to be so, because what we are hoping to give the user is something that they really don't have to think about other than providing the integrand and the error tolerance. So thank you very much. If you're interested in the slides, they are on Speaker Deck. And of course, I look forward to your questions and comments, either through the chat or through email.